Welcome to Roshan Academy, Learn and Succeed. Today we are here with a one-shot video on periodic classification of elements, your chemistry lesson from CBSE X textbook. Students, this video will not only help in concept clearing related to all the matters in this lesson of periodic classification of elements, but will also serve as a quick revision for your final examination day. That means you can use this video before your final exam for quick revision. Now let us move to the topic. We have already learned that matter around us is made up of molecules, compounds and mixtures. If you go through all these in details, all these contain individual elements in different compositions. Have you ever wondered how this world of chemistry or the world of elements have come up? See, scientists kept discovering various elements and then they felt the need to arrange these elements or to classify these elements by following some pattern or by following some proper order. For this, the first attempt, that is to classify the elements, was done by John Wolfgang Dobereiner. I repeat, John Wolfgang Dobereiner. You have to study this spelling properly, children. He used atomic mass to classify the elements and named them as traits, that is Triads. Okay, so we can remember this in shortcut like this: John Wolfgang Dobereiner, atomic mass, traits. So these are the key words that you should remember. Again I repeat, John Wolfgang Dobereiner, atomic mass, traits. Now we all know that atomic mass of an element is a mass of one atom of an element expressed by the unit U as recommended by the IUPAC. Now what is this IUPAC? Its full form is International Union of Pure and Applied Chemistry. Okay. Now Dobereiner started classifying the elements. He saw that certain group of elements, when arranged, that is in a group of 3, if the elements were arranged, they showed some similar properties. When arranged in increasing order of masses, atomic mass of the middle element was roughly the average of the other two. Now what does that mean? Let us see with the help of an example which he has given. Now lithium, sodium and potassium, if you see, the atomic mass is lithium 7, sodium 23 and potassium 39. Now what he said, you have to arrange them in increasing order of their atomic masses, and he has already arranged them, and he has taken 3 elements which are showing some similar properties. That also is correct. Now after arranging, he is saying that if you add up the first element's atomic mass with the last element's atomic mass and divide it by 2, that is take the average, whatever answer you will get, that will be the atomic mass of the middle element. So let us see. So 7 is the atomic mass of lithium, 39 of potassium. If you add them up together and divide it by 2, the answer that you will get is 23, and he is correct because the atomic mass of sodium is 23. So he was correct. But then why did this classification fail? There comes a point. Okay, his classification failed because he was not able to arrange all the elements known at that time in the same order. That is, taking pair of 3 elements having similar properties and arranging them in this order, and above that the average also should be equal to the that is the average of the first and the last element should be equal to the atomic mass of the middle one. So this was not applicable for all the elements, or he was not able to fit all the elements under this particular rule, and that is the reason why his classification had certain limitations. Now, what were his limitations? Let us see. He said that all the elements known during his time could be classified under this particular rule, but then he was not able to classify. Let us see why he was not able to classify with the help of an example, and that itself is the limitation of his classification. Now take another example of three elements showing similar properties: nitrogen, phosphorus, arsenic, with the atomic masses 14, 31 and 75. Children, try to do it at home. Now nitrogen atomic mass plus arsenic atomic mass, that is 14 plus 75 divided by 2, means taking average, you are getting 44.5 as the answer, and that answer should be equal to the atomic mass of the middle element, that is phosphorus. Now if you see phosphorus atomic mass, you may be knowing, is 31. That does not match with the average that we are getting, that is 44.5 is not equal to 31, and that itself was the failure of his classification. That means his law or his rule was not applicable for all the elements he knew at that time. Okay, out of the elements known at that time, only 9 could be classified as per the Dobereiner's traits. That is, only 3 traits were possible, and this was the failure or limitation of Dobereiner's traits. Now, even though if Dobereiner got stuck up by just classifying 9 out of 25 known elements, it paved a way to other scientists for better classification. Now here comes our next scientist, wizard John Newland, who was a British scientist, and he was working as a chief chemist of sugar refinery in London. He arranged the then known elements from hydrogen to thorium in increasing order of their masses. Interestingly, he found a pattern which could be connected with the 8 notes of music, that is the octaves. Now in India, the 8 notes that we have studied or we know is sa, re, ga, ma, pa, dha, ni, sa. Whereas in Western countries, if you see the notes, same notes, but then they are told or said in the way of do, re, mi, fa, sa, la, te. Here, the last sa resembled the first note in the octaves. That is, the same relation was seen in every 8th element. That is, the 8th element had the properties similar to the first one. Here, one more advantage of his classification was that he was also successful in fitting Dobereiner's triads correctly. Dobereiner was not able to fit all the elements in his triads, but now Newland was able to do that also correctly. So that was a successful thing as far as his classification is concerned. But yet, he was not 100% perfect. It also had its limitations. Out of the 56 elements known to him at that time, the law worked, that is his law of octaves, Newland's law of octaves, worked only for few. The law failed beyond calcium. That means this law of octaves, or the relation of the first element with the 8th element, was correct only till calcium. Multiple elements were arranged in the same slot because he purposely wanted to fit these elements into his law of octaves. As a result, he arranged CO and Ni, that is cobalt and nickel, of different atomic masses in the same position. Children, you can see that in this table very clearly. Now, what happened by this arrangement? These cobalt and nickel of different atomic masses were arranged in the same position, and that too in the same column with chlorine and bromine, which were completely different from cobalt and nickel. Hence, cobalt and nickel were a misfit in that particular column, and that was the limitation of Newland's classification. Further, Fe, that is iron, had the similar properties to Co and Ni, that is cobalt and nickel, and this iron were having similar properties. But then iron was placed far away in that particular table, so that was another limitation. Similar cases were with Ce and La, that is cerium and lanthanum. Another hit or limitation to this law of octaves was discovery of inert gases or noble gases. Being inert, noble gases had totally different properties compared to the other elements, thus could not be accompanied anywhere. Their existence shifted the position of other elements, means it could disturb the existence or the position of other elements. For example, hydrogen and fluorine are a part of same octaves, which is not disturbed by which is now disturbed by helium. If you put this inert gases with them, then they will disturb the position of the elements. Newland could not rectify or did not know how to place this inert gases, and that is the shortcoming of his law of octaves or shortcomings of his classification. Now, at that time came another hero from Russia, that is Dmitry Ivanovich Mendeleev. Dmitry Ivanovich Mendeleev. At that time, he knew 63 elements. He reacted each elements with hydrogen and oxygen to form compounds. The reason behind choosing these elements was that they reacted very easily with all the elements that he knew. While writing the formulae, you can see in his table everywhere the letter R, capital R is used. For example, RH4 for CH4, that is hydride of carbon. Now what does this R stand for? R is used to represent any of the element in the group. So that is a speciality of his table, that is he has used the letter R there. Now, during the process, he realized that some elements and compounds share similar properties. For example, lithium and sodium were soft and shiny, and were, when reacted, then reaction takes place, they form oxides on reacting with oxygen, and they also were reactive with water to form hydroxide. This made lithium and sodium friends, that is, he placed them together. He placed such groups in the table. He arranged them in increasing order of atomic masses. He saw a particular pattern there. Now what was that? He could see that sodium placed below lithium after a group of 6 elements. Potassium appears below sodium exactly after a gap of 6 elements. While arranging in this order, he saw that elements were automatically getting arranged in the increasing order of their atomic masses. This was something that he found out. For example, mass of carbon is 12 and nitrogen is 14.01, oxygen is 15.99. So order of the atomic masses, if you see, it is like a pendulum. It's going like a pendulum, or it is in a period, it's in the form of a period, or you can say it is recurring, or it is increasing. So from that he concluded, or his law was made. That is, his law states that period of elements are properties of elements are periodic functions of their atomic masses. Because of this periodic arrangement, he called his table as periodic table of elements. Now, structure of his table. Vertical columns, he named them as groups, and horizontal rows as periods. The gaps in this table were his predictions. Now you can see there are certain gaps there. So that he had some predictions, and he was very smart. Okay, so he knew that some new elements will be discovered in future. So he had some future plans also for the elements that could be discovered later on. That means he knew something about some elements, but he was not sure. So he had left gaps for those unknown elements. Which would exactly fit in that particular gap. He also gave name to this unpredicted or undiscovered elements. That is, he named them as Eka boron, Eka aluminium, and Eka silicon. He was correct. Later on, this Eka boron was named as scandium, and this Eka aluminium as gallium, and Eka silicon as germanium were actually discovered. So there he was successful. His prediction was correct. Now, the noble gases which were the villain in the Newland's octaves, Now, even during Mendeleev's time, the noble gases were not discovered. But the beauty of his periodic table is that the noble gases could coolly be occupied at the extreme right end of his table without disturbing other elements. Once these elements were discovered, so that means in his time this noble gases were not discovered, but then his elements were fitted in a correct manner, and so noble gases could be placed at the extreme end without disturbing these elements. That is what I want to say. At the same time, he placed heavier elements with before lighter elements, or we can say heavier elements were placed before lighter elements. If you see the table carefully, I am talking about pairs of elements. I'll be talking in pairs. Aluminium and silicon, if you see, they are coming very close. They are placed very close. Now, vanadium and chromium also, if you see, it is down in the next line that you can see. It is vanadium and chromium are also placed together. Similarly, you can see cobalt and nickel also coming close. This was done to ensure that the elements with similar chemical properties will always stay together. Since this was the basis of his classification, he did not want the elements to get disturbed, that is, he wanted to place them together if they have some similarities. Now let us move to the limitations. Now the limitations of his table was that between any two consecutive elements, the mass difference was not the same. It had a huge difference. Now let us once again see the table, then you will understand. Cd, that is cadmium with 112 as the mass, and Sn, that is tin with the mass 118. There was a mass difference. You can see the difference is 6 units. And at the same time, just go and see at the In, that is indium 115 is present between them. That means you can see cadmium, Sn and In. On the other hand, if you see, you have to explain this, let us see an example. Go to the table and see it very carefully, children, because to understand this you have to connect whatever I am saying with the table that is given. Now Cd, that is cadmium 112 mass, and Sn, that is tin, has a mass 118. Okay, now the difference here between cadmium and tin, you can see the atomic mass difference is 6 units, and In, that is indium 115 is present between them. Now this is the connection that you are getting between cadmium, tin and indium is placed between them. Okay, even if the atomic masses of 6 difference is there, unit difference is there. On the other hand, if you see Sb, that is antimony, or you can say the Latin name is stibium. Okay, it is having the atomic mass 112, and Te, that is tellurium, is having the atomic mass 128, has a mass difference of 6 units, but then it doesn't have any other element coming between. Whereas in the earlier case, you could see cadmium and tin was having indium in between. But now here there is no element coming between stibium and tellurium. So that was a limitation. So the problematic part of his periodic table was that between any two consecutive elements, the mass difference was not fixed. That is, if at one place it was fixed, the other place it was not fixed. This made it difficult to predict exactly how many elements could exist between two consecutive elements. Now another limitation was related to hydrogen. He was confused exactly where should hydrogen be placed. It should be placed with alkali metals or it should be placed with halogens. Mendel was not able to crack such type of questions. So that was another limitation of this periodic table. Now children, you must have observed that in case of all these three classifications, the common factor between Dobereiner's or Newland's or Mendeleev's classification is one single thing, that is atomic mass. Now, could you think that can this atomic mass be another reason for the failure of their classification? Let us understand that by understanding the modern periodic table. Now, let's move to the man behind the modern periodic table, that is Henry Moseley, a bubbling scientist who came up with a solution to all the problems that were there in the earlier three classifications. Henry was a crazy scientist who studied Mendeleev's table's beauty, and at the same time he tried to find out the flaws in the table. He thought that instead of atomic masses, atomic number should be used as a standard for arranging the elements, because he felt that it could be a better way out to arrange more elements accurately. Thus was framed the modern periodic law, which framed the basis for the modern periodic table. It states that the properties of elements are the periodic functions of their atomic numbers. Now, you may get a question coming up for exam that why did he select atomic number instead of atomic mass, or why was his classification, that is modern periodic table, successful by selecting the atomic number. Now, the answer for this is atomic number is unique and increases by 1 from one element to another. Now, how can you explain that? Say they are telling you to write an example related to this. You can write example, boron is having atomic number 5 and fluorine is having atomic number 9. Obviously, only 3 elements with atomic number 6, 7, 8 can exist in between them. So, which are the elements which are having atomic number 6, 7 and 8? You already know it is 6. That is the atomic number 6 is for carbon. Then nitrogen is having 7 and oxygen is having 8. So, between boron and fluorine, we can have carbon, nitrogen and oxygen fitting correctly, and then the order is completed, that is 5, 6, 7, 8, 9. There is no obstacle in such type of classification. The middle element here between boron and fluorine is carbon, nitrogen and oxygen. Now, another advantage of this modern classification over the Mendeleev's classification is that Mendeleev found problem in arranging aluminium and silicon because he used to consider atomic masses. Now that problem has been solved because here we are considering atomic number, and then in that case aluminium's atomic number is 13 and silicon's atomic number is 14. So that problem is also solved. Another problem that Mendeleev table, if you see, the isotopes did not find a place. But now here isotopes are also finding a proper place. Here classification was based on atomic number. So they were able to place the isotopes together in the same position. No problem even if the masses of the isotopes are different. Also, isotopes are having very similar properties. So it makes sense in putting them together and it does not make sense in putting them separately. So they were put together. Now, if advantages are asked, you can write down these points related to the modern periodic table. It is easy to remember the properties of elements if its position in the periodic table is known. So, this table is able to make us remember all the properties related to elements. The periodic table has made the study of chemistry systematic and easy. The type of compounds formed by an element can be predicted by knowing its position in the periodic table. So these are the main three advantages that you can see as far as the modern periodic table is concerned and the other three tables are concerned. And there are many other points, like they were able to classify isotopes properly, then atomic number, when it was started considering, many problems related to atomic mass was also solved, because in the earlier three table atomic mass was considered, and that is the reason why they were getting stuck up. Now here in modern periodic table atomic number is considered, so it becomes very easy for classification. I have given some examples also related to that. Now let's move to the main features of modern periodic table. Now when I am explaining this main features of modern periodic table, children, you can open the modern periodic table given in your textbook and see, and then study it one by one, listening to what I am saying, because that will always help you to comprehend the concept better. Now the modern periodic table is having these features, that is, elements are arranged in the increasing order of atomic numbers. So remember one thing, earlier three scientists, it is atomic mass that they were considering, and that made them stuck up or get stuck up. And then here in this table it is atomic number, remember, modern periodic table atomic number, like that you have to remember. Now elements in the modern periodic table are arranged in 7 periods and 18 groups. Horizontal rows are called as periods and vertical are called as groups. Elements are placed in periods based on the number of shells in their atoms. Now let us learn about the 7 periods in detail. The shortest period is the first period, which contains only 2 elements, hydrogen and helium. The second period contains elements from lithium to neon. The third period contains element from sodium to argon. Now I repeat, children, when I am explaining this, you have to keep the table on one side and then listen to this explanation through your earphone or whatever. Okay, now the third period contains sodium and sodium to argon. I said sodium to argon in the third period. Second period, lithium to neon. Fourth period, it is potassium to krypton. Fifth period, rubidium to xenon. So when you are by hearting this elements coming under the periods, first, second, third, fourth, like that. So first hydrogen, helium. Second, lithium to neon. But don't forget to write the word 2 there. Okay, third it is sodium to argon. Fourth it is potassium to krypton. Now fifth it is rubidium to xenon. Sixth it is the longest period. So the shortest period is the first one and the longest one is the sixth one, and it contains elements from cesium to radon. Seventh period is an incomplete period. Now let us talk about the third B, that is in group third B you are having under the sixth period you have lanthanides, and in the group third B of the seventh period you have acetinides plates. Lanthanides and acetinides are shown in the bottom of the periodic table. Okay. Now let's understand the 18 vertical columns known as groups and understand its features. So features of the long form of the periodic table. Light metals, that is, these are the elements of periodic table under the group 1 to 5. That means light metals are placed under the group 1 to 2. Now heavy metals, they are also known as transition metals, and these metals are arranged from in the group 3 to 12. That means 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All if you see, you will be having heavy metal or the transition metals. Now non-metals will be from 13 to 17. That is 13, 14, 15, 16, 17. And zero group, you will have the elements of the period coming under group 18. Okay, that means zero group is coming under 18th group. Now children, as far as remembering the name of the elements or the symbols or the chemical name and all that is concerned, you are concerned to remember only 20 elements of the periodic table as far as your 10th standard exams are concerned. But now how to remember the names of these elements? There are some shortcuts, and there are so many shortcut techniques given. From that I am giving you one or two techniques to remember the first 20 elements of the periodic table. Now if you see, we start with hydrogen, helium, lithium, beryllium, boron, like that you start, and you have 20 elements. So it's not easy to remember these 20 elements. For that I am giving you a shortcut. I have given the name of the elements along with the atomic number, and you can say the atomic mass, everything, so that from this you can even study that also. Plus you can study the name of the 20 elements in a shortcut way. To remember the first 20 elements starting from H, that is hydrogen, helium, like that, instead of by hearting the names like this, we can frame a sentence and remember it. So there are many ways then, and you must be also knowing one of these ways. So the first way to remember is hydrogen starts with H, helium starts with He, lithium starts with Li, Be, that is beryllium, starts with Be, boron starts with B. So you can see I have already written it down. You can understand it and you can by heart it. But when you are studying this, just write it down once again and see. And after writing, just keep on saying that particular sentence again and again. So then you will remember H stands for hydrogen, but He stands for helium, like that. Be stands for beryllium, but B stands for boron. Now if you see like that, so many are there. C stands for carbon, but Cl stands for chlorine. Al stands for aluminium, but Ar stands for argon, like that. So for that you have to remember this shortcut sentence that I am saying. Okay, now the sentence is like this. Happy Helen like beans but cannot obtain from near. So here happy, the first letter of happy, H, stands for hydrogen. Then Helen, Helen is a spelling. So He, the first two letters, stands for He, that is helium. Like, Li, stands for lithium. Beans, beans. Be stands for beryllium, like that. Okay, now I'll read once again. Happy Helen likes beans but cannot obtain from near. So here you are learning the first 10 elements. Now what about the next 10 elements? Let us see. It is नानी मांग अलका से Pepsi, soda, cola or kaju cake. Now this is in Hindi. Okay, so remember na stands for sodium. Mange, so M-A-N-G, mang it is. So mang, M and G you have to take. Mg stands for magnesium. Alka, A-L, starting two letters, it will be aluminium. Se, so S, take it, it is silicon, like that. Okay, so this is the way you are remembering. So I'll repeat once again. It is Happy Helen like beans but cannot obtain from near. Next is Nani Mang Alka Se. You can write SI also if you want, but it is Se. That's why I've written like this. Pepsi, soda, cola or kaju cake. So this is the shortcut to remember the first 20 elements. There are another shortcuts also. Some children may not say it in this way. They may say na mang Allah se Pepsi, soda, cola or kaju katli. That is also another way of saying. There are so many short forms like that to remember the first 20 elements. So children, now in this slide you can see electron distribution in the orbit and what are the name of the shells given. That is also explained in detail, and some examples are also given so that you can understand how the structure of the different elements can be and how the electrons are arranged inside the shells given there. Now let us go through the trends in the modern periodic table. Now the periodic properties can be arranged in the form of atomic size, valency, metallic or we can say electropositive charge and electronegative charges. Now first let us see what is the meaning of atomic size. Atomic size means it is a distance between the center of the nucleus and the outermost shell of an isolated atom. Now what happens to this atomic size as we go across the period and down the period? Let us see that. Atomic size decreases from left to right along a period due to the increase in the number of increase in the nuclear charge. Whereas if you go down the group, atomic size increases down the group due to the addition of extra shell as we go down the group. So this is what is happening as far as atomic size is concerned. Now let's move to valency. First, see what is the meaning of valency. It is the number of valency electrons present in the outermost shell. Or in simple words, we can say that it is a combining capacity of an element. Now what happens across the period and down the group to this valency? Now changes across the period. For the group 1 and 2, the valency is 1 for the group number 1, and for 2 it is 2. Now for groups more than 10 valency elements is calculated, that is the electrons are electron is calculated by the formula group number, that is minus 10. Means, for example, for group number 16, the valency electron will be equal to 16 minus 10, that is equal to 6. Now down the group you will see that it remains the same. Now metallic or electropositive charges. What is the meaning of that? It means to lose electrons to form cation or positive ion. Now across the period decreases because atomic size decreases. Now down the period what is happening? Increases because atomic size increases, hence it loses the electron easily. Now non-metallic property, or we can say electronegative charges. What is the meaning? It means to gain electron to form ion or negative ion. Now it increases across the period and decreases down the group. So this is the trend in the modern periodic table. Now let's learn electronic distribution of orbits. Arrangement of electron in atomic orbital is called as electronic distribution. Now if you look at the electronic distribution figure given there, you can understand that in the center we have the nucleus, and the first circle, or we can say the first circle, is called as the K shell, and the next one is L shell, the third one is M shell, and the last one is the N shell. Now in this figure you can see along with the shell, that is K, L, M and N shell, in bracket N is written there, N equal to 1, N equal to 2, 3 and 4. Now what is this N? N is the number of given shells for the nucleus. Okay, it is the number, that is the ring number that is given. Now let us learn how many electrons are there in the first, second, third and the fourth period, and how can you find it out. We can explain the number of elements in the period based on how many electrons are filled into various shells. You will find that you have learned how to calculate, or we can find out the accommodation of the shell depends on the formula 2n square, where n is the number of given shells for the nucleus. For example, let us take K shell. In K shell we can say n equal to 1 and the formula is 2n square. So in place of n we can write that 1. So 2 into 1 square will become 2. Hence, the first period, I am talking about period, the first period will have 2 elements. Then next is L shell. 2 into, here n is 2. So, 2 into 2 raised to 2 will be equal to 8. Hence, the second period will have 8 elements. In this way, the third, fourth, fifth, sixth and the seventh period has 8, 18, 18, 32 and 32 elements respectively. The position of an element in a periodic table tells us about the chemical reactivity. As you have learned, the valency electrons determine the kind and the number of bonds formed by an element. Now let us do a quick revision of what we have learned. In the first part, we have learned the classification done by three great scientists that we can call it at in the earlier period. Okay, so that already we have explained, Dobereiner, Mendeleev and Newland's classification. And then we learned the modern classification done by Henry Mueller. I have explained the characteristics and name of the groups. Now one more thing that I have to explain is SPDF. Now SPDF here, SPDF means S block, P block, D block and F block. Now let us see which are the groups coming under it. Group 1 and 2 elements are called as S block elements. Group 13 to 18 elements are coming under P block elements, in which metalloids and non-metals are present. Now group 3 to 12 elements are called as D and F block elements. So that is the meaning of SPDF. Now that also has been explained. And next was the trends in the modern periodic table, that was explained with the help of a chart, or you can say with the help of a table. So children, now we are done with the periodic classification of elements, your chemistry lesson. You can use this one short video for quick revision before your examinations. Please like, share and subscribe.